In this lecture, we're going to go into a little bit more depth in relation to SUPG, the Streamline, Upwind, Petrov-Galerkin method. And I should actually start with correcting myself a little bit. I think I said that the method was introduced in 1983. It was actually 1982. And well, what I certainly was not incorrect about is that this was a very important work. I looked it up just now, and it has well over 6,000 citations. Yeah? So this is a very highly cited work, and maybe one of the most cited works in all of finite element literature. So what I'd like to do today is kind of look into this name a little bit, because it might be a bit of a confusing name. It's certainly a very long name, and it has some more difficult terms in it, right? Streamline, Upwind, Petrov-Galerkin. So okay, this idea of streamlines, that's something that we had a bit of a feel for coming from the notion of the streamline diffusion, where we said we're adding a consistent, variationally consistent diffusion term that doesn't act in all directions, right? It doesn't diffuse, it doesn't add artificial diffusion in all directions, but only along the streamlines. So okay, that's I suppose the part that we're kind of okay with. But how about this Upwind Petrov-Galerkin? That sounds a little strange. So that's something that I try to motivate in this video. So let's take a closer look at the formulation, and there's actually one thing that I would like to highlight here, and that is the fact that we have second derivatives in our residual. So let me just rehearse, right? We have our classical finite element term, so this b being equal to the right-hand side, that would be the Galerkin method, and now on top of the Galerkin method we add this residual-based stabilization term, right? So there's a residual here, defined as per the lower line, that it has a stability parameter in here as a multiplication, and then some operation on the test function. And this is very easily consistent, because if the true solution is substituted in this equation, then the residual will be 0. Okay, so now I want to focus on this residual term and the second derivatives in there. And actually that's a bit of a problem. Let me go a few steps back here to remove some of the underlines. Yeah. That's a bit of a problem. Remember that, so we're looking for test and trial functions in our space W. Start already. Come on. Okay, maybe I'll just change the color here. Ignore the problem. So we're looking for solutions in the space WH. And that was a subspace of our Sobolev space, which was H1. So these are functions for which the first derivative is well defined. Right? And in our finite element context, we're actually creating this subspace as this sum of, for instance, hat functions, these linear hat functions. Right? And we always like to draw this in 1D because then it's easy. So now in this residual, we're making use of a second derivative. Well, in principle, we're not allowed to do that, right? So that's because we're dealing with this Sobolev space H1 on our domain. So second derivatives are not, by definition, well defined. And it's actually the case that for our finite element approximation space here, they are not well defined. What I can do here is I can take one derivative, and then in each element, I have my functions become constants, piecewise constants. So that's still fine, right? So that's this first basis function would become something like that. Let me draw one more here. I'll also draw it over here. So that's something that looks like this. Right? So they become these step functions. So that's well defined. That's also a function that I can square and integrate. So this resulting derivative function is a function in L2, which means that the original function was in H1. Now, I can, however, not perform another differentiation on here. And the reason for that is not what happens inside the elements. Inside the elements is fine. I can take the derivative of a constant function. That would give me simply a 0. That's fine. And also on this side I would get a 0. The problem is on the element interface. If I take the derivative of a step function, that is not well defined in the classical sense. And we'll actually get back to this in future classes or videos. We can interpret this in a certain sense, but for now I want to go with the claim that that's not well defined. So the operation that we want to do here is not an operation that we're actually allowed on the complete domain omega. Right, this is on the complete domain omega. So what we're going to do instead is we are going to say, well, we're not going to do this on all of omega. We're going to do this on K, the element domain, and we're going to sum over all elements. And maybe a nicer way of writing this, more complete way of writing this, we're going to sum over K in, and then we have typically, oh, that's maybe a bit confusing in this context. Let me write it like this. Where we have the elements K in this set curly T, where this set curly T is the set of all elements or element domains in the mesh. So I'm adding a sum over the element interior volumes. Now, and inside of each one of these elements, so inside of this range, and this range, there my operation of the second derivative is well defined, and I'm not doing this on the interface. Now, that might look like a bit of a trivial point, but it's actually important for the thing that I want to say next. And that is that we're going to rewrite this term a little bit such that we get the interpretation of this Upwind Petrov-Galerkin. That also shows up in the name. So what we're going to do is we're going to actually perform integration by parts again on this last term in our residual. So let me zoom into the added term, right? The residual based term. So that's going to be written as f times tau a dot gradient w. Let me make sure that the signs are correct. It's probably a minus, yeah. Minus, and on each one of the elements, right? And then we have now a plus, if I'm not mistaken, a dot gradient of phi h, tau a dot gradient of w. And this is again a minus kappa times Laplace operator on phi h times tau a dot gradient w, also on the element interior volume. So now I'm going to do integration by parts on this last term. And that will give me one volume term, okay, gradient phi h times the gradient of, well, whatever was in here. And technically, because we're now doing this on the element interior, I would also get an element boundary term. That's a minus. So we would get kappa times the gradient of phi h dotted with n times tau a dot gradient of w. And that's the term that we actually get now because we're not allowed to perform this thing on the complete domain, right? So that's why it's not really a trivial point that I was addressing a second ago. We're really not allowed to do this on the complete domain because if we were to do this on the complete domain, then we would be forgetting about this term in a certain sense. Okay, so now why am I doing this? Okay, so if we look at this, and I would now sum over all my elements, right? Then this is going to actually be equal to the original bilinear form. Now let me start with the original linear form minus L. What was the linear form? Well, that was F times W. It was a linear form on W, right? So now it's not F times W, it's minus F times tau A gradient W. So this is the linear form A dot gradient W. Plus, am I saying this right? I feel like I'm not saying this right. No, that's correct. Okay, plus the bilinear form. Well, all of these were the same terms that we had before as well. Right, those were originally in our bilinear form as well. And now on the right lid, so this is simply going to be phi of h. But on the right lid, I again have this tau A dot gradient W. Right, so because these terms, they're the same bilinear form, they form the same bilinear form as the original bilinear form, A dot gradient phi times some function, and kappa gradient phi times the gradient of some function, where now in our case this some function, what originally was a test function, would now be tau A dot gradient W. And now actually we have this additional term plus, I'll call this simply a boundary term, PDY, boundary term. That is somehow also a bilinear form that depends on phi h and w. And that's a bit of an annoying term, really. And that's the term that I would like to forget about the point that I want to make, that this is sort of an Upwind Petrov-Galerkin method. So that's actually incorrect, what I'm going to say. But I think that's something that they might not have realized when they proposed this name. The fact that this term would still have to be there in order for this to be a Petrov-Galerkin method. So I think it's important that I do address this, that there should be another term here. But I still want to also make it clear why we're calling this an Upwind Petrov-Galerkin method. Okay, so if I now use this form, this representation of this added term here in this equation, and then what that equation ends up looking like is what we have b of phi h and w plus b of phi h tau a gradient of w plus our boundary term is equal to L of w plus L of, can you see this? Yeah. Go a little bit down here. Plus L of tau a dot gradient w. Okay. Now, due to linearity of our bilinear and linear forms, I can actually collapse this a little bit, and I would get b of phi h w plus tau a dot gradient w plus still this boundary term being equal to the linear form of w plus tau a gradient w. And now I will forget about this boundary term, even though that is really not correct. So if we ignore the BDY boundary term, then we would get a new finite element formulation that says b phi h w plus tau a dot gradient w being equal to L times w plus tau a gradient of w. So what I can do now is I can say, well, these are just gonna, I'm just gonna interpret these guys as my new test functions. And then I can write this as b phi h. So let me be complete now. So originally I would say search for phi in the space WH such that this is true for all test functions W in the space WH. But now I'll rewrite this a little bit and I'll say find my solution phi H in, well, still that space WH, such that the following holds are bilinear form times a new function, which I will call, we'll just use V. So I introduce a new test function such that this is equal to L of V for all V in a new space, VH, where VH, where, remember that WH was the span of a couple of basis functions from I is equal to 1 to the number of degrees of freedom, right? Those will be these linear head functions. So WH is the span of these linear head functions. The span means that any linear combination of these head functions is in that space. So it's a vector space by definition. And now my new space V is going to be equal to the span of Nix plus tau A dot gradient of Nix. Right, because I've replaced this original statement here with the green underlines. I've replaced those expressions by new test functions. And if we use these new test functions and we want to have the same expression as our original SUPG formulation, where we've forgotten about the boundary terms, then the space for those new test functions V should be that original space plus now this additional operation on each one of the single basis functions. So now we're looking at a finite element formulation where the space for the trial function, our solution function, phi h, is different from this, the function space for our test functions. And if we use different function spaces for the trial the solution functions and the test functions, and then we're dealing with a Petrov-Galerkin method. Yeah, so that's why the interpretation of SUPG as a Petrov-Galerkin method comes from. It's from this rewrite, where we're sort of forgetting about one term, and then you can rewrite this showing that you would actually use sort of Petrov-Galerkin basis functions here. So that still leaves one term though. We talked about Streamline, we talked about Petrov-Galerkin. So what's with this Upwind? And actually this Upwind is connected to Petrov-Galerkin, so this should be an Upwind Petrov-Galerkin method. So let's take a look at what these new basis functions then look like. Yes, I'm going to say, so this is going to be equal to the span of new basis functions, which I'll call L and tilde. So if my original basis function looked like this, a simple linear head function, so this is going to be n, then n tilde is going to be equal to n plus tau times the advective velocity dotted with the gradient of n. So at each point I'm interested in advective velocity. Let's say that the advective velocity, we're talking about a one-dimensional case here, right? I'm simply drawing one-dimensional basis functions. So let's say that the advective vector points to the right. So we have A to the right. So that's going to be dotted by the gradient of n. So what's the gradient of n? Well, that was the first derivative. We already saw what these guys look like. That's this and this. And if we dot that by the vector that points to the right, then that's still going to be equal, that's going to be positive here and negative on the right. So this is going to be A dot gradient of n. X. So this is nx. And so our new basis function. And what does that look like? Well, this one still needs to be weighted by our stabilization parameter tau. And what that would look like is now a function that is the sum of both of these. So that would actually be a function that looks like this. Depending on our choice of tau. Depending on our choice of tau, this difference between the left and the right part would be either larger or smaller. So again, this is a Petrov-Galerkin method because for our trial functions, our solution functions, we're using basis functions that look like this. But for our test functions, we're making use of basis functions that look like this. And again, our vector velocity comes here from the left. And this is now why we call this an upwind Petrov-Galerkin method. Because in the upwind direction, we're adding additional weight to our test function, to our weighting function. And in the downwind direction, we're actually removing weight. And maybe I should draw this a little bit more careful because, of course, this should be doubled. So we'd get something like this. Yeah, so this is why this is called an upwind Petrov-Galerkin method. Okay, that's I think all I wanted to illustrate in this video. Get you a little bit more familiar with the name here because it sounds very complex, and I hope that with this video that's clarified a little bit. So thank you for your attention.